sound. But not exactly, because sound needs molecules to travel and light doesn't. Anyway, we think that like sound, light and other electromagnetic waves can also be squeezed and pulled apart when a space object emitting these electromagnetic waves is moving towards the viewers. That'd be us here on the Earth, or away from us. So if a star were theoretically moving really fast towards the Earth and thus squeezing its light waves, like the train whistle being heard as a higher tone than the one that it emitted, those light rays might be observed as a yellow frequency, though what was being emitted was orange or red. And of course, the opposite might also be the case, where the star emits green, but what we see is red or orange. That would mean the star is redshifting, or moving away from us rapidly, like the train whistle changing from a higher pitch to a lower one, with longer waves due to the broadening of the waves by the receding train. But how do we know that the star isn't just giving off yellow or red in the first place, without the shift? Now that's the million-dollar question. And the answer to that one takes us back in time to the Napoleonic Wars around 1800 and a guy named William Wollaston. He was trying to figure out a good scientific method for analyzing gunpowder for the British. He would burn the gunpowder and watch what happened to the rainbow that was created from the burning gunpowder passing through a prism and projected onto a flat piece of paper behind the prism. It wasn't until much later that Niels Bohr and Erwin Schrödinger reasoned that the dark lines that would show up in the spectrum of separated colors were packets of energy at specific frequencies being absorbed by electrons in the atoms. Bohr coined the term for these single jumps of energy, quanta. Thus, these guys began a whole new branch of science called quantum physics, all about this bizarre phenomenon of energy being emitted or absorbed in discrete packets without any blending. These dark lines that showed up in specific places in the spectrum were always in the same spots for each element. When burned, each element always gave off the same number of lines, called spectral lines, and always in the same spots in the spectrum. That meant that once you had figured out the signature pattern of spectral lines for an element, you could recognize its presence in an unknown sample, much like the way human fingerprints can reveal who must have made them. Even today, when a scientist analyzes an unknown substance, they burn it, and the light from the flame passes through a prism or diffraction grating, and the position of the emission lines or absorption lines in the spectrum tells the scientist what elements are present in the sample. This instrument is called a spectral analyzer. So if you add a prism or diffraction grating to the telescope's viewing apparatus, it separates the star's white light into the rainbow. You can then find out what elements are burning in the star. Using Wollaston's idea of a prism separating light and observing spectral lines, the German physicist Joseph von Fraunhofer in the early 1800s observed these dark features, absorption lines, in the optical spectrum of the sun. These were later termed Fraunhofer lines. We see these not only in the sun but also in stars. However, in the stars, these lines, undeniably created from the same elements, are located slightly down, lower in the frequency in the spectrum. In fact, in 1929, Edwin Hubble, yes, the very same one that the Hubble Space Telescope is named after, proposed what is now known as Hubble's law with its constant of proportionality, Hubble's constant. What he found is that all the stars in space are redshifting or receding from us. Not only that, the further the stars with known distances using parallax were from us, the more redshift they showed. So the further away, the faster they're moving away from us. Aha! Does that mean that we are at the center of the universe? I knew I was right when I was 3 years old. Nope, sorry, you're wrong. Think of it this way. What if space itself were expanding? Then that would mean that everything is moving away from everything else. That's what most scientists now believe, that space is expanding or inflating, and it expands more the further its edge gets from you, or for an observer anywhere in space. Thus, those waves of light from the furthest observable stars are pulling apart so much that the spectral lines of the elements burning in those stars are moved the furthest into the red end of the spectrum, and perhaps even below the red, into the infrared. This is what Hubble's law does for us. It gives us a ratio to use of how much redshift a star displays, and how far away it must therefore be. Now, as unsubstantial as this explanation may seem, it has been cross-referenced and calibrated with at least 5 other distance measurements, probably the main one being an amazingly consistent candle power of type 3A supernovae. Okay, so the furthest reaches we see is in the tens of billions of light years. Well, just how far is a light year? How do we know? And where does this come from? A light year is how far or the distance that light travels in a year. What? Light has a speed? When you turn on a light switch, the light just turns on immediately, right? How could it have a speed if it's immediate? For a speed to be a speed, it has to take some time to occur. Otherwise, there is no speed. The first people to measure the speed of light with any accuracy were some Frenchmen in the 1840s, Armand Fitzhugh and John Foucault, also the inventor of the Foucault or Earth pendulum and the gyroscope. The way this contraption worked was Fitzhugh placed a really strong light source on a hill in Paris, along with a system of lenses arranged so that the light reflected from a semi-transparent mirror and focused on a gap in a toothed wheel. On a distant hill about 8.63 kilometers away, he placed a mirror that would reflect the light back to be viewed by an observer. The toothed wheel was rotated and the speed of the rotation was varied. The light only became visible when the rotation speed was such that the reflected light passed through the next gap in the wheel. So the time for the wheel to rotate through the angle between successive gaps equaled the time for the light to make the round trip to the distant mirror and back. He recorded a speed of 194,000 miles per second. Later, Fitzhugh's method was improved by John Foucault. He replaced the toothed wheel with a rotating mirror. Light would strike the rotating mirror and would be reflected to a distant fixed mirror and then back to the rotating mirror, and finally observed through a telescope. The speed he finally gets with this new improved light measurement device is 186,000 miles per second, or 300,000 kilometers per second. That's about 7.5 times around the Earth in a second. And this is so accurate that he then is able to measure a difference in the speed of light when it slows down ever so slightly in water. Okay, so if light travels at 300,000 kilometers per second, that means a light year can be calculated by multiplying this speed times 60 seconds per minute times 60 minutes per hour times 24 hours per day times 365 days per year, and that gives you 9.4 trillion kilometers. And finally, here it comes. Drum roll, please. The current space distance record, 122.2 billion trillion kilometers. That's 20 zeros after the 2. From Mr. Crowder's World to you.